Now, so far, the only two examples that I've looked at were examples that were parabolic in nature. I don't want you to think those are the only types of functions that we could have. So let's look at what happens if we have a semicircle. Okay. So if we have a semicircle, let's say with a radius of 5, and the reason I say a semicircle instead of a circle is if we have a circle with radius 5, of course it's not a function. So we want to avoid that by saying we don't want the bottom half of this circle. We want the top half of the circle, radius 5, okay? And what happens here? Well, what I'm going to do, because this is a section where we're talking about volume, the circle is a two-dimensional object. I'm going to rotate it around the x-axis, which is going to make a three-dimensional object called a sphere, right? We know that. We know what a sphere is. We have plenty of experience with spheres in our lives. We know what a ball looks like, right? So I rotate it and I form this ball. Now, how do I turn this into a case where I can use a volume, this rotation to get the volume? Well, I look at this and I say, well, what is this function, first of all? Well, at some point in time, you learn this, which in our particular case would be that. And so to solve for y here, y squared equals 25 minus x squared, y equals the square root of 25 minus x squared. And again, to truly solve this, we would say plus or minus, but we would be, including the bottom end, it wouldn't be a function. Here it's a function, and we're rotating that around the axis here. If you rotate that around that axis, then again, what you want to look at is an individual slice perpendicular to the axis. And if you notice that, again, distance from here to here is going to be the radius, right? There's going to be some itty bitty tiny circles over here. There's going to be the big circle here, but there's going to be a bunch of different circles, okay? And so when I look at this, I say, well, an individual circle that I pull out of there, what's it going to look like? It's going to go from the center here up to some y value. That's r. But again, when I am doing a slice in this direction, that says that is a delta x. If that is a delta x, that means my integral is going to become a dx. If that is a dx, everything must be in terms of x. So I look at this and I say, well, I don't want r to be y, I want r to be in terms of x. But I know what y is. Y is this. So, okay, but what I really want is I want the area pi r squared. And since r is that, r squared is that without the square root, and I left out the pi. Again, to actually do this integral, I'm going from 25 minus x squared, pull the pi outside. And what's my integral from? From where to where? Well, if I'm going to get this entire semicircle, I got to start over here and go to here. I'm going to go from -5 to 5. When I do that, what happens? Again, it's a simple integral, 25x minus x cubed over 3. And I integrate that from 5 to -5. And I can see there's some symmetry there. I could have gone from 0 to 5 and gone twice as much, right? Because it's going to be the same on each side. But 25x is going to give me 125 minus 125 over 3. And then subtract off at -25, -125, minus and minus like that, plus. And you see, in fact, we did have that symmetry there because this is going to become a plus 125 minus 125 over 3 when I distribute there. And I end up with pi, of course, and I end up with, to get a common denominator here, 375 over 3 minus 125 over 3. And then distributing that, I'm going to have exactly the same thing here. Moving just up here, pi times 3, so that looks like 250 over 3. This is going to be 250 over 3, so 250 plus 250 over 3. And that looks like pi, 500 pi over 3. That's what we end up with. Okay. Now, if you know what the volume of a sphere is, which here we didn't use the volume of the sphere formula, but we could have. The volume of a sphere, 4/3 pi r cubed. Well, we had an R of 5 here. If we plug that in here, what do we have? 4. I've got the pi, I've got the 3. R cubed. Well, 5 cubed. 5 times 5 is 25 times another 5 is 125. 125 times 4 sounds a lot like 500. Now you could say, well, you could have just done this in the first place. But I could say to you, you didn't have this formula necessarily. You didn't know what this formula was until somebody did this. Somebody did this generically and said, if I just let that be R right there, then what happens here is I end up getting 4/3 pi R cubed. If we hadn't said what R was and we just had an R in there, that's what we would have ended up with, which is where the formulas like this are derived out of calculus in order to get those formulas, like formula of a sphere, formula of a right circular cylinder, formula of a right circular cone. All of those come from a place like this. We have them the other way because that's the easy way that doesn't require calculus. That's the result. What we generally have in the back of the book or whatever, even at a lower level than where we are now, is we would have in the book formulas for these things. But those formulas came specifically from a place like this.